Yes, sir.
All right, I'd like to welcome everybody to an exciting day for all of us. I know I've been waiting with great excitement for Dan's defense here. So he has pulled off an amazing miracle in my mind. I don't know how you do what he has done, is what you're going to hear about here, and work full time. And at least from my perspective, I'm in ultrafast optical technology. So he and Mike and Gungwo have been really schooling me on these signal processing techniques that we could apply to significant ultrafast optical problems. And he's really achieved that here. So it's going to be an exciting afternoon to see if we can actually process this. And he's done it, yeah, all the while working. So it's and hopefully we actually have him around a little more in the area to kind of continue on these endeavors, because it's really been a game changer for us. So with that, he's going to give a presentation, and then at the end of his talk, we'll open up the questions to the studio audience. And once those questions are done, everyone is excused, and it just goes to the committee asking questions. So with that, let's go ahead and welcome Dan. Here's his report.
Thank you, Jeff. I appreciate the introduction. I've been kind of rearing up a bit. It's really nice to get out in front of you guys and present and defend some research in structured inverse problems in ultrafast optics. As Jeff said, I'm Dan Rosen, and has been passively introduced on this slide. I've been at Mines for a long time. I've had some involvement, at least going back to 2012, a couple years off in the middle. But this is sort of my preferred place. I don't really get out too much. I'm pretty academically inbred, as it said, but it's just because I enjoy being here so much. So that said, I'd like to get into the presentation. And start on the back foot and actually issue a correction for my thesis is the first slide of this. I apologize, I know you guys have read it. However, chapter 5 starts with phase retrieval from integrated intensity of auto-convolution. Article under revision submitted to signal processing. It should say reproduced with permission from an article in signal processing less than 36 hours after I sent it to you guys. Of course, it's when it was accepted, and I literally have to do no time stamps just because I can't. So good on them. They're real good people over there, so I'm happy it got in through the 5 reviewers there. So as all good defenses should answer, what does this research contribute to signal processing and optics? What are the difficulties involved and the risks that were taken? Why was specialized signal processing required to solve this problem? And what is my personal involvement in making that secret sauce? You're going to see this chart, there we go, kind of throughout. So the 5 years that I've been here, we've had our hands in a number of different problems that all kind of lead up into our study of pulse characterization. Throughout, you'll kind of see this, and I know it's a little bit hard to see in the back, but basically it's major events. The two that I like to highlight are the proposal, which happened in early 22, and right now, this defense right here and right now. And the proposal is kind of central to a lot of this stuff and a lot of the good work we were doing on these problems. So this chronologically fits the story that we're going to kind of tell today. If you guys have seen Dunning-Kruger charts, it's always good to acknowledge that little valley of humbling that comes throughout all of this, confidence versus experience and time and so forth. And you have, good days and bad days.
I noticed it doesn't quite come back up.
The red at this point to be, a smidge underinformed. That's all right. That's it. We'll get right into it. So what are structured inverse problems? Most of us are familiar through linear algebra, the concept of an inverse problem in general. I have something y that is linearly related through something like a matrix to a variable x that I'd like to know about. And typically, if you satisfy things like the invertible matrix theorem, you should be able to get back to x using something like a matrix inverse. However, there are special circumstances of these problems, broad categorical problems like being overdetermined or underdetermined. And in the case when you're underdetermined, the classic response is always you don't have enough equations to satisfy the number of unknowns that you'd like to resolve. except there are ways around that. For example, if X occupies a low-dimensional subspace, that is that X has only a few non-zero values inside the entire vector, compared to its size, you can solve underdetermined problems by encouraging something called the L1 norm. So you have two terms involved in your minimization, a measurement fidelity term, which just says you should be close to the measurements that your system produced, and a data regularization term, which says that it should satisfy certain constraints. In sparse processing and compressive sensing, this started out as the L1 norm, but it has since evolved as problems have evolved. For example, semi-definite problems take on nuclear norm under the condition that matrices are positive semi-definite. And again, it still follows this general form. You got to be right in the sense that your answer has to match the measurements, and you have to be right in the sense that your answer has to make sense. Sometimes it means be simple. Sometimes it means be low rank. We're going to see throughout that rank plays a huge portion in pulse characterization. Another type of structure that we're going to talk throughout these problems is I'm going to turn out the lights because the colors get a little washed out. Is a structure of landscape. So we have some problem landscape, right, where any number of answers can live throughout, and we want to get to the top of some hill called cost. We want to get to the bottom of some hill called cost. Now, we have tools that help us. We're not just blind in this wilderness. We have a notion of local slope and local curvature. These functions are called gradient and Hessian, respectively. Now, let's see if this will play. Oh, that's good. Ultrafast optics studies little light pancakes in some sense, but basically lasers have been condensed to the smallest time scales that we can get to, basically on the order of sub-picoseconds. And this is not every ultra-fast pulse, but this is a good representation of at least ones that were used in the lab, at least at Focus. And that's good. What's special about these pulses, besides the fact that they're ultra brief, is that they are ultra powerful. And to get an idea of how powerful they are, I have a handy little chart here. There's a whole bunch of powers on this chart that we all have, of course, intimate knowledge of, right? Like we're all familiar with how much the human brain consumes. But that said, there's a couple of powers on this chart that I'd like you to maintain. For example, this is the region of ultra-fast pulses. And if you notice, there are a couple of powers that are commensurate with that. Like all of humanity's consumption at a given instant is on the order of the power contained inside one of these very, very short pulses. And that is approaching the amount of power that the sun radiates to the earth at a given instant. And as you might suspect, this is useful for all sorts of interesting physics, like accelerating particles to ultra-relativistic speeds, or imparting a ton of energy in a short amount of time. To get an idea of how much time, that's what the second chart is for. One number I keep in my back pocket is that 1,000,000 years is to 1 second, as 1 second is to some of your run-of-the-mill ultra-fast optical pulses. The really, really short pulses that are nearing dozens and tens of attoseconds are to 1 second as 1 second is to the life age of the universe. So really, really short pulses. That's sort of the thing to get out of it. But what can they do? They can do things like fusion. So the National Ignition Facility last year achieved net positive power out of a fusion reaction, and it did so with some number like 192 or 96, I can't remember what, some multiple of that. Lasers being focused onto this little cylinder called a holoron, and it causes fusion with this whole X-ray plasma wave that compresses matter inside. Now, that said, we don't use it for fusion, we use it for things like imaging. And that's really satisfying to someone who's in signal processing, because we're familiar with problems like imaging because they tend to fit this linear form. This is a really basic description of a system called SPIFFy that we kind of got our start in studying. Basically, a slit of light is spatially modulated at one end of the system and concentrated onto a sample. And the light that passes through this sample is collected on a sensor. And as this wheel spins, it encodes a unique series of information on that row, and signal processing should be able to get it back out. Now, for the most part, really simple processing is all you need. For example, an FFT on that collected data, I don't know how well you guys can see. We're going to play a game called Optometrist with the audience. All right, image 1 or image 2? 2, good. Image 2 or image 3? Oops, 2, 3. Right. That
I didn't mean to right click there at the last minute.
What's nice about this problem is it's something that we can all access, but unfortunately for sparse processing scientists, or optimists as I'll call it for short, is this problem's been solved by the practitioners. You talk to Randy Bartle's group, you talk to the Minds Optics department, and yeah, we know sparsity improves images if you do it right. We understand there's algorithms like FISTA, there's algorithms like iterative hard thresholding, and as long as I understand my forward, yeah, I can do this myself. And so, okay, this is sort of our bread and butter of processing, is applying sparsity. We're going to have to look for an interesting problem at the crossroads of this elsewhere. And a good gateway problem to that is called diffractive imaging. There's a whole categorical slew of these problems. But for continuous waves, the idea is that a continuous spatial phase beam of light illuminates a sample, and you can reconstruct that sample from its far field diffraction. Now, unfortunately with that, we are modulating, we are imprinting on our sample with a wave that we can't measure directly. We can only measure intensities. And so that means that we don't have a linear problem anymore. We have a nonlinear problem. And so the optimal science of phase retrieval is what's used to recover X from Y. Now, a little problem with this is you can never know the true phase of X. You can only know relative phase. So there's a couple of ambiguities in this problem, but for the most part, that's not a deal breaker in any science. A fascinating addendum to this problem is the idea of broadband diffractive imaging. Diffraction is itself a narrow band phenomenon. When you start talking about multiple wavelengths, now you're talking about multiple incoherent images that will add on top of each other. There are some phase retrieval approaches that adapt to this very nicely, and we'll talk about that later. But that core analogy is the same analogy that exists between how we originally did pulse characterization and the new form of pulse characterization that we discovered. So what is pulse characterization? This is the problem that we landed on. Pulses are imperfect. They are awesome, they are condensed, but they are not perfect. They can be stretched through materials as they are dispersed, is the word that we'll typically use for that. They can be tilted, they can blemish, they can have some radial effects that are associated with them. However, trying to get a handle on them, trying to measure on them is very difficult. And I say that from two separate perspectives. The intensity problem I've already mentioned to you guys. We can't measure wave phase. We have to measure things in intensity, so we lost phase. However, the lifespan of these pulses is so short that they are beyond, between a factor of 5 and 50,000, the speeds of even the fastest intensity samplers, right? So you can go to Tektronix, buy yourself a 200 gigasample per second detector, and you're still only about a fifth of the way there. You need to go faster, and we're not even talking Nyquist probing at this point. We're just talking hoping that you get a handle on it. So too fast to measure, and we measure in intensity. These are problems. However, there's a really neat solution, and I have to say up front, light does not travel like little pancakes. Light constantly diffracts, but this is a good idea of how second harmonic generation happens in a crystal. So the idea is two pulses can meet inside a crystal at the same time. And if it produces second harmonic generation, what that means is that the crystal will absorb 2 photons of light of one wavelength and re-emit phase synchronous with the original light, a single photon that is half the wavelength or twice the frequency. And we can use this to tremendous effect, but the most interesting of these is that we can use a pulse to multiply another pulse. How convenient is it that we don't have a shutter that's fast enough to perceive the events that are happening, but we can time synchronize pulses to overlap with each other and act as their own shutter, light measuring light. The only problem with this is that the structure of our phase retrieval problem is way different now. It's not just the intensity squared of AX. Now it's a phaseless quadratic. It's not a phaseless linear problem. So that introduces a complication, not a deal breaker. So at this stage, especially in the thesis early on, I like to introduce a hierarchy of problems up to this point, and their main differences from linear to the first nonlinear problem to the second nonlinear problem. And on the right, I like to introduce a complication caused by incoherent overlap. This is your lensless cameras or cameras that have some sort of spatial spread function or blur, the idea that multiple far fields can overlap on multiple measurements. The second, and this is the equivalent sort of analogy for diffractive imaging, is that broadband diffractive imaging I was talking about, where you're not trying to invert X from just one phase retrieval problem, you're trying to invert it from a blurred phase retrieval problem. The same is true with our primary contributions in pulse characterization. The original problem, linear with respect to the fourth order outer product tensor, is solvable with Bertinger gradient techniques and with tensor techniques. However, there's an analogous problem that comes from integrating over wavelength, reducing a two-dimensional data set to one that is solved with those same techniques. And we'll get to this one. This one's a little bit funny. So to start out, we have our challenges and our risks established. We have a phaseless quadratic problem that we'd like to solve. There's a fairly small literature from the signal processing community on it, and almost all of it centers on a version of pulse characterization called FROG. There's related science that's heavily studied from phase retrieval, but it's distinct. Some of the lessons carry over, but not all of them. And at this point, this is probably right around early 21, we're a little bit nervous just because of how many variations of the second order problem exist. There's intensity of auto-convolution, there's intensity of cross-correlation. It would be nice if we came up with an answer that addressed those generically, didn't have to care. Now, the main risk at this stage for us is we know that there are sparse problems in the other sciences that we've been studying, but at this stage, there's only suggestions that there may be a sparse answer or an optimization interesting answer at the end of all of this, and much less an answer that's useful to optics. And so the big risk at this stage is we don't know how pool this deep goes. How pool this deep goes. How deep this pool goes. We don't know how deep this pool goes. Okay, we're lucky in the sense that the problem had been studied before. And there's three kind of big categorical techniques on how to do pulse characterization. And there's one simpler approach that exists for doing it purely in intensity. This is an autocorrelator. But to start with some of the closest to, I guess, the sort of starting problems that you'll end up working with. Interferometry is a really neat one. This is a picture of something called Spider, but basically involves two pulses interfering, and you can use transform domains to find things like differential phase. So for example, you take the spectrum of two interfering pulses, you take it to time using an FFT, you get the autocorrelation function, and that first correlated peak. This is very close to cyclostationary processing, if anybody's rearing and wanting to make analogies. The second one, I actually see the least amount of literature on. This is tomographic methods. If any of you are familiar with a CAF function, its two-dimensional Fourier transform cousin is called the Wigner function. And Wigner functions have this really neat property that if you measure a signal, its intensity in time or in frequency, you've taken a marginal of that Wigner function. And so tomographic techniques, you try to make a sport of rotating the Wigner function using some sort of transform and taking marginals to reconstruct it. But the most interesting to us are called spectrographic techniques. And this is where this problem of FROG has lived. The idea is you're taking cross sections of this Wigner function. And with FROG, at least with a duplicated version of the pulse itself, we're looking at purely intensity of the Wigner function every time we take a FROG measurement, which is nice. Now, FROG is the most popular, and I'm going to argue that that is because of the algorithm that it's packaged with since the late 90s when Dan Kane wrote PCGPA. But the process basically goes like this. Inside an autocorrelator, a pulse enters and is split into two pieces. One path goes up and one path goes right. Now, these pieces are allowed to have a very similar path, but you can control precisely how much delay is on each channel. They're brought back together again, and they're crossed inside a nonlinear medium, and we measure the spectrum of that. Now, there's two basic axes that we can measure at this point. One is the spectral axis of the spectrometer. So every time we take a measurement, we're taking a new spectrum. And we control relative delay. And so we build up this two-dimensional data set, which is, through transforms, related in intensity to the Wigner function. And we can apply this really neat trick called PCGPA. But this is not the only way we can do spectrographic techniques. There's other systems. FROG is very useful, but it's a little limited. We want something more generic, and spectrally modulated, spectrally resolved systems like DScan, like Spark, give us that opportunity with something called zero dispersion pulse stretcher, or a Martinez compressor is the way I've always seen it written. And it allows us to generalize this problem to the intensity of quadratic functions, just like we know that they are. So for example, we have x and we have y. These are functions we would like to find, but we don't have access to directly. C and D are modulations that we either get to control or we have to live with, depending on the nature of the problem. And we can condense all of this into something that's more pleasant to look at, subjectively, of course. Which is a quartic function that looks just like a multiplication of two quadratic terms. I can differentiate that all day, and in fact, we will do that later today. This is nice. This is really neat, but it still doesn't explain why frog was so much more popular than we expected it ought to be. And I think it really comes down to this algorithm called PCGPA, which is ahead of its time. By leaps and bounds. It is an early version of a low-ranked matrix problem, and it goes a little bit something like this. So when this problem starts, what we want to find is E1 and E2, but we don't have direct access to any of those variables. What is interesting, however, is every row of the frog dataset that is collected, so this would be single delays, full spectrums, is a phase retrieval problem with respect to a diagonal of the outer product of E1 and E2. So we can't touch E1 and E2 directly, but we can recover faceless versions of the diagonals of E1 and E2, which is great. If we have all of them together, an SVD should be able to get us back to E1 and E2. There's a problem. Phase retrieval does not return global phase. And so that means that we're going to get back these diagonals, but none of them agree with each other on what matrix they actually belong to. And so step 2 is a thresholding operation where you split the matrix into its eigenspectra, you hold only the top, left, and right eigenvectors, and you reconstruct the matrix from only those. And you iterate back and forth between these two processes. A phase retrieval technique for the diagonals, force it to be rank 1. And you carry that phase information back to your phase retrieval problems, and you do this until you get a rank 1 answer. And it works phenomenally well. So we're going to reinvent the wheel a little bit with this one, unfortunately. And the reason that we're able to is because we can pull new lessons from phase retrieval research. And there's a bunch of lessons that apply, but I'd say 3 are the most influential. The simplest one is called Wertinger flow. The idea that because you can write a nonlinear problem like this as the product of purely complex variables, you should be able to apply Wertinger calculus to this and do gradient descent. And in fact, you can. There's variations of this problem that involve magnitude versus intensity, but they're all related to taking just a Wertinger gradient of a cost function. The second lesson, this will sound familiar, assumes that you're doing phase retrieval on a problem, but you don't quite have enough to invert it. But what you know is that the signal that you're watching and trying to do phase retrieval on doesn't vary a lot. It varies in a low rank way. And so this was a method to stitch together a lot of phase retrieval problems. Sounds very similar to PCGPA. Now, the final lesson isn't actually the best way to do phase retrieval, but it introduces a really beautiful concept called lifting. The idea of lifting is that you can take your nonlinear function and you can force it to be linear, not with respect to x, but with respect to something else. And in the case of phase lift, it was linear with respect to the outer product of x Hermitian, which is very interesting because that lesson extends to higher order number storage units. So things like tensors. And we can actually see a little bit of this process kind of drawn out. I'm a cartoon-oriented fellow. So this is our nonlinear function. We have y, and we have a matrix inside on x. Let's just focus for now on one little number inside y. We know it is the intensity squared, or sorry, just the intensity. Gotta get my units right there. It is the intensity of an inner product, a sub I, just one of these rows, with x sub 0. However, we know we can write any intensity as the product of a number, which is what this is, and its own conjugate. However, the product of inner products is equivalent to the inner product of the outer products of their inners, which is fun. And I can't say that 10 times fast, so I won't even try to. But what's nice is this looks really gross. We can't really handle this with simple techniques, but we can handle this with simple techniques, but we've just caused a huge problem for ourselves. X was small. X naught is not small, it's squared with respect to the size of its original problem. So we're back at underdetermined problems, which goes all the way back to slide 2 of this. We know how to understand and apply under determined systems. Now, how do we adapt that lesson to PCGPA? Well, first, we're going to start with one diagonal and recall, there we go, that one diagonal is itself just a really basic phase retrieval problem. Now, we're going to apply that same technique that we learned from phase lift to this problem. So we're going to study one little dot here, it can be any of them, but with this diagonal, we're going to write it as the product of something in its conjugate. We're going to combine the inners with an outer product, as now it's just a linear inner product now. And we're just going to make that look like a matrix. It is a matrix and it's rank 1, but this is going to help see where it fits in later. Now, at this point, when we were studying this, we really wanted to see if algebraically there was a way to try to combine information from these different diagonals that we were covering. And there kind of is, it's not super effective. But what's nice is that there is a space where you can recombine them. And to understand where that space is, we have to get another outer product in here. So we start by vectorizing the outer product that we're trying to recover into a vector. And now we take this matrix turned vector and we look at its outer product with itself. Well, this new outer product diagonal matrix that we've recovered actually belongs to this space as part of a block diagonal. And so it sits a little arrow right there. And what we see is that this problem, which we've generically named intensity of cross correlation, ICC, is a mask. We can only measure properties of this fourth order tensor from this block diagonal, which does sound like a structured problem. I have something that I know should be low rank. The only problem is when I try to apply something like an SVD to this, because it's block diagonal, I get chunks out. There's nothing that encourages these chunks to be one with each other. And so I need something else that actually stores these. But at least we have something nice that orders these measurements as a linear inner product, right? So for example, positive lags, a little bit forward on the block diagonal, negative lags, a little bit back, and central lag, of course, is on the main diagonal. We've made this a linear problem, but this is not the space to properly view a fourth order outer product. To do that, you have to get a little bit creative. Okay, just fun. This, if it's hard to visualize, I apologize. It's difficult to try to get into four-dimensional stuff, but it's admirable to get your foot in the door. So this is a random tensor of a 7 by 7 by 7 tensor. There's 7 tensors. They have each 7 dimensions, and this is just random at this point. Right now, color is encoding for phase, and intensity is communicated by brightness or opacity. They're kind of the same for this shader. Now, we can do a lot of things in this space. For example, a phasor that you take an outer product of 4 times doesn't really look all of that organized until you see it from certain angles. We can actually make this a little bit bigger. If it's okay, can somebody on Zoom tell me if you're able to see this? Daisy, perhaps, maybe on the chat. Okay, if not, that's okay. Ooh, there we go. Nope. Okay, hey, thanks, Dan. I appreciate that. But so we're gonna go ahead and new share. How about now? Yay, there we go. All right, and I'll go back to sharing the slideshow in just a moment there. Okay, so perfect. This is what a tensor looks like in our mind, and this is just a really simple outer product tensor. Okay, we can look at ones, which is less interesting, but to look at the actual measurements that we're going to touch using ICC, we can actually apply a mask. Now, this is structure. This is something neat. And in fact, we can even color it by what diagonal of the outer product it is going to solve for. White, in this case, is the main diagonal. Yellow is a positive diagonal. Blue is a negative diagonal. And red, the rat value, is the last corner values of the outer product matrix that we're going to be solving for. So that said, this definitely looks like a structured object. And if we apply something like a higher order SVD, we should be able to get something out of this now that isn't just a little fragment of a block. And so we're going to go ahead and return to this later. I'm going to go ahead and stop the share. And we're going to go ahead and go back to the old slide deck. Okay, perfect. Let's go ahead and begin. Not going to start through that show again. Okay. So what we can absolutely show is that this problem is an inner product on fourth order tensors. And if you collect all of those problems together, they make something that looks an awful lot like a regular old linear algebra problem. And we know that the answer has to be rank 1. And so now we can apply a structured inverse problem to this. And the way that we do that is actually something called iterative hard thresholding. So really simple approach to all of this. Take whatever guess you have, forward project it to your measurement space, take its error and back project that back to your fourth order tensor space, and then enforce that that tensor that you're looking at has to be the outer product of 4 vectors only, and you just keep doing this until you get the right answer. Now, this is not the correct way to view this problem, but it is mightily convenient to view this problem in that sort of unwrapping. And what we can actually see is how this problem solves for things. So this is the signal tensor. Obviously, we start mostly unknown. We know a little bit about block diagonals just because it got forward project or backward projected. We can watch the error decrease over time, and the dashed signals are what we'd like to recover. X and Y are both low bandwidth signals, and our first guess is obviously wrong. It's these solid lines. It's just a pulse, and we know it should be something broader. This is differential phase, differential comparative phase to be sure, and we just want this to be a flat line. We can explain more about that later, but let's go ahead and watch. And sure enough, it seems to converge to it. Cool, we have a technique that can do this. Of course, while that looked cool, it would be very, very neat to see a bigger version of that. Hot dog. And what I really want you guys to look at is try to think of like nucleation of ice or something like that. It's the only thing I can really compare it to. And it spreads out. It starts in one spot and delocalizes. And I'm just going to go ahead and speed things up here. The only thing interesting that happens is that this main diagonal is going to get a little bit more crisp. But we get the right answer doing this, which is really nice. We fill up a whole big tensor just to solve for 2 small vectors. And if that sounds a little bit inefficient, it's because it is nice that it can work. But we need something that's a little bit more practical and bread and butter in this case. And that is where, oops, come on, there we go. Vertinger gradients come back. So if you guys have taken a gradient before, there's nothing to it to make that into a Vertinger gradient. And all that means is that you're now differentiating with respect to complex variables. You don't have to do anything cumbersome like differentiate with respect to real or imaginary parts. Instead, all you have to do is take derivatives of your original function with respect to a variable and its conjugate, put them inside a row vector, and take their conjugate transpose, and that is now your complex gradient, your Vertinger gradient. And there's simple adaptations that turn this into a function of purely real variables, so it can be adaptable to all of our favorite things like SciPy, minimize, things like that. And there's even more cumbersome definitions for Hessian, but they exist. So cool, we have a gradient of real functions that can be taken with complex variables. Now all that really remains is to pick a good cost function with respect to all of this. And there's 2 choices at this point. One of them is probably the newer, sexier cost function, and that's the magnitude cost function on bottom. But we have good reason at this point to stay aligned with the pure intensity cost function, and that is because it leads to a new cost function that we studied in our second paper. We'll get to that in just a moment, but first, let's get into the Vertinger gradient. So the way that we actually take it, remember there's 2 variables that we have to work with. Originally, we took just a gradient with respect to both and stacked them, and that gets incredibly cumbersome. So instead, what you do is you concatenate them and you modify your problem so that it's only a function of 1 variable. And now we can apply differentiation to really simple things like cost functions that are built from least squares, right? We know all of these answers ahead of time. We apply things like chain rule. Nothing breaks. It just gets big, and it does boil down eventually, but what matters out of all of this is that we get a list, a recipe to calculate cost, gradient, and Hessian. And what's nice, at least about this, is we look at our expressions for things like gradient. When error is 0, when we're on the right answer, the gradient goes to 0, exactly how it should work. When the Hessian is at ground truth, so when error is 0, it's comprised exclusively of a sum of positive outer products. That means it's positive semi-definite. We've done our job. This is good. Now let's actually apply it to some data. There's a lot of charts here. All of them are built in the same way. We're going to go through them a little bit at a time. The vertical axis on all of these charts is the number of measurements that we started with. The horizontal axis is the size of the signal we are trying to recover. And what we want is this red region, which means failure, to be as shallow as possible. We want more blue on this than we have red. We want this to be as shallow as possible. And classical techniques like PCGPA are right here. They work well, but there's a nice line that separates winning and losing. Tensor techniques were tested, and from what we can tell about them, they seem to do a little bit better than PCGPA. The only problem with them, if we look far on the right here, the time it takes to actually run them, I have to plot in decibel seconds. And if anytime you have decibel time, you are looking for that time. Right? So yeah, let's see, 4,000 decibel or 4,000 seconds per run on some of these, and so that gets a little cumbersome. You need something a little faster, and thankfully, Vertinger techniques just come to save the day. They totally whoop on all of the other methods that we have up to this point, with one exception. It all depends on how you start them. When they start randomly, they still do really well. When you start them with PCGPA, they don't really seem to change. But when you start them from the tensor IHT that we just watched, they do better, which is interesting. That means that they contribute some information to each other that the other didn't have. Or maybe tensor techniques had it all along, but it would have taken years to have found out that sort of information. And it actually, from this chart, we know that that's not true. So they contribute to something together that makes them a really efficient algorithm, even more efficient than the already efficient Vertinger approach that we were already taking. So at this point, it's time to apply it to real data. This is the Wilhelm paper on D-scan data. And if everything looks like the same in this picture, good. It's exactly how it should be. We did get the same answers. We did get the same results. We were more stable than alternating minimization in this sort of case. And it's not a super fair comparison. We really are operating right at the basic amount that you would need to actually solve this problem. So we shouldn't have expected PCGPA to do very well, but it's nice to see that our algorithm actually holds up in these low measurement conditions. Sounds like a paper. This was called bivariate retrieval from intensity of cross-correlation. And the main takeaways from this paper are that ICC, this intensity of cross-correlation, is a form of a problem that's previously been studied called low-rank phase retrieval. Gradient techniques really, really work well at it. Tensor techniques can even improve that performance. And techniques that we would have thought of trying first, called spectral techniques at this point, they don't work here. And in fact, they can't work here. The framework that we've discovered is adaptable to frog. It's adaptable to spectral techniques. It's adaptable to D-scan, Spark, things like that. So we've really kind of collected all of our techniques at this point to this existing problem, and we produced a paper which got accepted late last year. But this isn't a new problem. This is us solving an old problem in new ways. What happened here, this sort of epiphany region right here, is actually the discovery of a new way to do this pulse characterization problem built on a condensed data set. And to see where that condensed data set is, the easiest way to see it is in that tensor space. So again, this really kind of complicated, lots of bells and whistles problem gets boiled down into just a simple linear problem over two variables, I and K. I is changing for new modulations. K is a collection of lag indices. And in this case, for this problem, for spectrographic techniques, it is the wavelength index at the second harmonic bandwidth. And so what's interesting with all of the measurements that we have is that they're disjoint. None of them actually fall on top of each other. And because the problem's linear, there's nothing that's going to prevent us from adding them all together. And to see that, we can actually take our measurement and say that it is a sum over K. Well, that sum in tensor representation, nothing keeps it outside of that inner product, and it can easily be moved in, and this is still just a tensor inner product. And so all of these terms, all of these measurement tensors or modulation terms can be combined into one. And what was once a two-dimensional data set can now be solved as a one-dimensional data set. We can see if it works using IHT. This one looks a little bit different. I actually like the colors a little bit more. It does not go straight down like it used to, but if you give it enough time, it certainly seems to get there, which is interesting. It's cool that old techniques work. I wonder if Vertinger gradient techniques work. They do. And in fact, they look almost identical to the old ones, right? All you have to do is move a sum around. There's a couple of cases where you have an outer product that you have to add first, and then you have to add outer products after that. But for the most part, all of this is consistent and works. You can even numerically test it, and we did. There's red regions and blue regions. The thing that separates them looks like a weak quadratic line, which isn't the worst news in the world. What's nice is if you look at these lines, this is the 50% rate of convergence, 25 and 75% rate of convergence. Basically, how many times do you have to do this problem to expect to be right? Half the time, 3/4 of the time, and 1/4 of the time. The dashed lines here are randomly initialized, and the tensor initialized lines, the solid lines, seem to do better. So we get the same result again, that we have an excellent gradient technique, and it seems to do a little bit better when we have tensors initializing it. Now that said, those data sets that were two-dimensional were pretty efficient with the number of modulations required to get a 50% convergence rate. However, we know that every measurement was two-dimensional, and so it added a lot more pixels. ICC, or IIAC, I should say, this integrated approach, seems to split the difference. And so we have this nice trade-off now, but we still don't actually know what we have in our hands until about 4 months later. So this was something we figured out back in August of 21, and it wasn't until about Christmas that it really drives home the point that we're looking at. When you sum over the K variable for spectrographic techniques that aren't frog, ones that are like DScan and Spark, you are integrating over the frequency domain. And anytime you take a sum over intensity of frequency components, Parsifal's theorem says that it is the same as integrating over the intensity of time, which means that what we have now is a technique not to invert spectrographic data sets from a spectrometer reading. We can do inversion straight from a single pixel integrator, which condenses the setup drastically. Now we can try to apply this to a system that's only looking at the variation of energy of second harmonic generated pulses. Say that 10 times fast. Does it work? Yes, it does. So this works. This was applied in a lab. Thank you, Dan Scarborough and Jeff Squire, for building this, because I have no idea how to actually align and build a system like this. We want to see if we can see both pulses, and in fact you can, right? One right after the other. That's unfortunate. I'm sorry, people on Zoom. If you're with me, hang in there, brother. It'll be good. And in fact, we can recover a spectrum from this, and this is still just using a single pixel sensor. Now, this does sound like a paper, and in fact it is. This one was the one that was accepted, I believe March, it says right here, doesn't it? March 11th, right? Or March 6th, there it is. And the takeaways from this paper, phase retrieval from intensity of auto-convolution, is that IICC, this new problem that we're studying, is not like any other phase retrieval problem of high order that we've studied before. It's a new one. It's this incoherent sum over phase retrieval problems. Tensor initializers and gradient approaches can effectively solve for it numerically and in a laboratory setting. And in the context of optics, it represents a spectrographic approach to pulse characterization that doesn't seem to require a spectrometer, which is nice. In fact, we've actually tried to adapt this, and we're doing very well at this point to adapt this to new experiments to try to make a pulse laser microscope. And we have a new mask in here. We can talk about some of the features of it, but for the most part, it's packed full of features and should be able to do the job well. And in combination of moving a second D-scan screen to provide complex phase modulation, we've gotten some new results that are stable over degrees of freedom. We're able to measure pulse spectrum effectively and see it in time as well. And there's not much to look at here. This is just a compressed pulse and a compressed pulse. What's interesting is when you apply complex phase shifts on top of it. These are quadratic. They should stretch the pulse in time. And we get the expected value back pretty well. There's a couple of that one and that one. Just ignore those. I try to apply all of this with the same settings. I consider it cheating to cherry pick, to change the settings a little bit to make the plot look better. But what's nice is that we can recover this from sets that we're looking at, which are very small compared to what the actual curves say we should be requiring for this. So the fact that we're getting the actual quadratic phase that we're putting on it back is nice. We're actually seeing really similar, stable pulse profiles from multiple experiments. Excellent. Key answers now. Okay, so I think what we have answered here today is that the difficulties we had to overcome are just those involved with frontier topics. There's not a lot of people doing what you're doing. There's not a lot of places to go for help, but luckily there's an adjacent problem that we could pull a lot of analogies from. What risk was taken? There may not have been a useful compressive sensing technique or optimization problem to solve here. There was. I'm super happy that that's the case. Very, very happy that that's the case, but it might not have actually existed. So that's the risk of always associated with frontier research. Why is specialized signal processing required in this problem? Inverter gradients did a ton of lifting on this, and they've been demonstrated to be a very effective tool for inverting complex variable problems. Compressive sensing wasn't used to actually look for unique dictionaries. I went through a whole talk on compressive sensing and didn't mention like bases or anything like that once. Compressive sensing was used in this problem to undo a nonlinearity with lifting and then apply a very powerful data regularization term, which is that the tensor rank of our signal tensor should be 1. The actual personal contribution that I put to this then is then deriving gradient and structured tensor techniques to solve for laser pulse characterization inverse problems. Discovered a condensed technique to invert measurements from spectrally modulated second harmonic generated total pulse energy. And I wrote 2 papers on this topic with the help of amazing advisors, mentors, and co-authors. The overall contribution to signal processing then is a unique and new high order phase retrieval problem. And the contribution to optics then is a way to do spectrographic pulse characterization without the spectrograph. Future concepts that extend to this then, there's besides the pulsed microscope that we're looking to work on with Dr. Scarborough and Dr. Squire, is that we can try to carry this onward to spatiotemporal characterization, which just means that we're not looking at a single axis or the bulk axis of our pulse anymore. We're trying to apply this over multiple directions, which is nice because we've adapted this to a single pixel technique. An array of 2 pixels should be able to provide us with a ton of information. I'd like to extend this beyond second harmonic nonlinearities. If a intensity of a quadratic problem can be solved with 4th order tensors, I have high hopes that the intensity of a cubic problem or a third harmonic generation problem and beyond can be solved with an order 6 tensor and similar vertical gradient techniques. And then finally, to bring it back to compressed sensing, to actually study domain sparsity optimization. We have a pulse that's condensed in time, which means that total variation or similar norms in spectrum should be cleaning house. They should be absolutely kicking this problem and doing very well. We also know that there's known spatiotemporal couplings, and so this problem of spatiotemporal characterization, we're not out in the cold on this one. We have prior to work with that we should know and expect in these problems. Now, that said, I'm not only superstitious and a little bit eccentric, but I'm also nostalgic and romantic, and I have people to thank for supporting me on this project and throughout my life. Obviously, number one, first and foremost, my wife, Jackie. Hello, Jackie. Thank you for helping me set up snacks and, you know, being married to me and all that sort of thing. Been best friends since we were Gravity Falls pre-teenage and together throughout and since. I really appreciate you being by my side. Nothing really seems worth it without you. So thank you. Also, I have never gone wanting for love or guidance my whole life. I have an awesome family. I have awesome in-laws and just people in my life that make this really painless for me. So I really appreciate that. Thank you guys, Rosen's Manilos. I also didn't have pictures. I like to this about. That's pretty good. Okay, it actually looks like math, which is what scares the hell out of me. So I'd like to thank my advisors, Mike Waken and Gongo Tong. I'd like to thank my committee, which extends to Jeff Squire, Dan Adams, and Tanner Vincent, and Daniel Scarborough. Thank you very much for making all of this believable with me. So this is the main crew I'd like to thank professionally. In addition to, as Jeff mentioned, I have another life and people that I work with and friends and coworkers. And if you don't see your name there, it's because I'm pig-headed and forgot. And I promise it was unintentional. So I want to thank that crew as well. And then finally, all of you guys. I'd like to thank you. And if this is a little small, it says I thought there would be snacks. Death by slideshow, right? And if you think that I chose this tie based on what an AI drawing of angry townspeople throwing tomatoes at a public speaker cartoon picked, you're absolutely right. Goku's basilisk is real. I served them first. There we go. So that's it. I would be very happy to open this up to questions to the general audience. If you don't have questions, I also have prepared.
That I might not be here, maybe
Like 30 slides.
Oh, yeah, no way I was gonna kill you guys.
Oh, yes, but I might forget it.
Sorry, Jeff.
Great question. Integrity. No. I actually did use neural networks. Right here, stable diffusion. So you can use neural networks for a whole bunch of really interesting problems. For example, this is the square root function. If you guys are unfamiliar with it, it takes a number and returns its square root. Not much to it. You can also complicate the heck out of it and make a 4x4 neural network with a tanh activation function optimized by LBFGS, and you can get a pretty agreeable answer. That looks pretty good. You can use neural networks for anything. It's true. However, when you already have the tool that's good for the job, use that. We know that we're pulling from an order 4 tensor. Higher order SVD should be the thing that actually pulls it out. We have a tool that tells us where the next best answer is. We have gradient. And so we use that one. So it is a really solid approach in problems that they are designed for. But if you have advanced a priori knowledge on your problem, always exploit that. There we go. I think we've had that conversation. I think we might have, Jared. Excellent.
Hi, Dan. Can you hear me? Hi.
Oh, wow. Sorry, I was looking around. You sounded like you're in the room. That's really cool.
Yeah. This is Ifan, so I'm on the Zoom.
Okay.
Yeah. I have a question. So you mentioned that the tensor-based methods are empirically better than the gradient-based method. Do you have an intuitive reason behind that?
So I'm uncertain at this stage if they're better. It certainly makes me hopeful that maybe they are, but if we look at the plot, that kind of has all of this together. Yeah, it's shallow and I don't have a whole lot of samples of it. And maybe it's better than the randomly initialized, or they perhaps are comparable to each other. It's their combination that really hit it out of the park with this one. And so I wonder if one is better than the other. The problem with tensor techniques is that they take a long time to run. And at this stage, I have a couple of results that relate to, the null space of them, but I don't have a strong theoretical grasp to how good they are yet. We have some numerical results, and we can talk about theoretical ones soon, perhaps if we like. It gets a little bit dry, but we will get there. But I don't think one is better than the other at this stage. I think that they're really good together. They're an excellent pairing.
I see. Yeah, but I saw that in your takeaway message in your in this one of the papers you presented perhaps in one of the slides. So I'm curious about what point you're trying to make for that.
Apologize. I need to turn up the volume just a little bit. Yifan, can you try saying that one more time? Sorry.
Yeah, I think you make that point in one of the slides, takeaway message for one of the papers,
Excellent. Back.
Scroll up. Maybe scroll up a little bit.
Scroll up.
Yes.
Oh, that's
Yeah.
there's
further up.
this result slide, and then
I mean 2 more. Okay. No.
I think he's saying one of the slides where you showed the paper.
Yeah, there's a paper. Yeah.
Let's talk about that.
Not this one. Let me see. Another paper.
Very good. I've waited one past them. Yes, right. There.
Yeah. Yeah, the third like bulletin point, tensor techniques work well and improve the performance of gradient techniques.
Yep. As an initializer, I should say.
Oh, I see.
Yes. As an initializer, we don't interrupt it at any point. We just start from the result that's produced by the tensor hard thresholding technique. Usually after just a few hundred iterations, we try to keep it pretty quick.
I see. Okay, thank you.
Oh, no worries. Thank you. I appreciate the question.
Are the tensor problems in the lifted, are they kind of like the facelifted versions?
Yeah.
So doesn't it have something to do with the convexity?
I assume that there is something about, so I mean, that's the thing that's kind of hard to understand about this is phase lift, the same application of this to phase retrieval, wasn't better. It was n log n when things had been shown to be order n. It wasn't better than the other techniques. And so I was kind of running under the assumption that maybe it was something like this bigger space, and maybe the strength of that tensor norm is so good that it squeezes something out. But I don't have a solid answer as to why it improves the gradient techniques, other than maybe it has some piece of information that they don't.
I was just thinking like philosophically.
Oh, yeah.
One is convex and one is non-convex, right?
Yeah. So funny that you should mention.
So
that.
is it the point that like the lifted techniques are pointing directly at the solution, whereas the other ones maybe pointing at like some global or local thing?
The convexity, I think, helps. The thing about phase retrieval techniques is that they are non-convex. It's very true. However, they're not that convex. And that's the one that's kind of a little strange. One of the theoretical approaches we did take during this paper was attempting to look at the expectation of our cost function. And that's where things get really strange. For phase retrieval, we can show that while it's non-convex, it's not bad. If you start within a reasonable ball around the right answer, and I mean reasonable as in like a factor of 10, you'll get there. And you'll get there with enough measurements. The result that we got from this was vastly less appetizing. And it's actually why I don't have a ton of theoretical results. But the story goes where if you have a cost function and it's a square of the difference of cortex, it is linear in a space, which is what we need to take an expectation of 8th order tensors. And so in this problem, what we actually ended up doing was taking an expectation of these tensors and trying to reduce their result, and they get just unbelievably gory really fast. This is just the cost, the expectation of the first two terms of gradient. And sadly, I do have the other terms, at least for the Hessian, in the simplest way that I can actually show them. I agree, this is probably ad nauseum, but I apologize. This is the simplest that we can actually boil down Hessian into, and it's just plugging in I's and J values. I tried for months to try to find any pattern in this, and trying to find patterns, while very soothing to humans, is not something that math always lends itself to. So this got messy pretty fast. But one thing that is consistent through all of these approaches, let's just take perturbation 6. I don't even know about that, but I think that's a piece of the smaller. No, I will not. A piece of the smaller tensor, right? Like two derivatives from x conjugate and y. What almost always creeps up when you try to reduce them, you get functions where you have x and y, good things that you should like, and then unanimously everywhere diagonal cross terms. And so that means we could never make a statement about where this equals 0 or where it was positive semi-definite without these ridiculous concerns about, oh, we can only make that assumption if x lagged with respect to y by 2 is non-orthogonal, right? Like we would get conditions like that. And the closest we got to actually making I'd say a concrete theoretical statement about this stuff is that we do know the null space of this operator, especially for IIAC. And it boils down to any modulation vector you have C, it can't jointly multiply with x to be 0. That's the only rules that we found so far that don't produce a null answer. If you have a situation where that arises, you can add anything to that space and you won't affect your answer, just like classical null spaces should, even on this nonlinear problem. I think I might have danced a whole circle around that question. I apologize. Oops, go back to the questions page. Yes, sir.
So you touched on the new mask that we've been working with in this a bit. And we've seen good results with those. There seems to be a favorite column. And I'm curious kind of what things are lending to that being better than the others.
I need to see if I actually grabbed it. I think I have it on my other flash drive, which is okay, we can look at it. So the column that you're talking about is number 11.
Good old number 11.
It's good old number 11. So there's a lot of masks here. Okay. There's a lot of details to this. Number 11 is the coarse dithered Bernoulli mask. So it's, let's see, it's one over.
Just before. Yeah.
There we go. It's that one. Yeah, it's random. It's weird and it's gross. Why do you use random bases to measure anything? I like to use random in circumstances where I'd like to guarantee that whatever I'm trying to measure doesn't correlate in some unknown ambiguity to what I already have. So for example, if you're trying to measure something using sine waves and it's made of sine waves and it's made of sine waves that are faster than your sine wave, you won't get any results because it's orthogonal to all of them. That's a problem. If you try to measure, say, with impulse functions, so we have a collection of impulses here, but your object that you're trying to measure is an impulse. Only one of your measurements will actually have any useful information, and that's not very useful to us, especially when we have gradient techniques that are built from multiple measurements. And so the Bernoulli mask is something that's random. It shouldn't correlate with anything, and it's on and off in equal measures. All of our results should be right in the same ballpark. So for optimization purposes, least squares leans heavily towards large measurements. This should produce them in the same ballpark. Now, that's not a good answer to why does this look like it's made of splotches. And the answer to that is I use a technique called dithering, and I specifically chose one that's called random dithering. To understand why dithering works and what it is, and when we build a mask with it, you gotta find a picture. Here we go. Really zoomed in. Okay, this is a good picture of dithering. So we want to modulate with this, but all we have access to are binary variables, 0 and 1. A really natural way to do this is just to round, right? Well, unfortunately, for problems that have spatial bandwidth or bandwidth concerns of any kind, true discontinuity contains an infinite amount of spectral content. And so you see, these will go down. And in fact, you see a little bit of a base floor. That's not real. That's aliased versions of this same wave wrapping. And now we can't actually look at a real representation of this space. There's something called Floyd-Steinberg dithering, which is a really, if you're into image processing at all, it's how newspapers make pictures out of 3 colors. It's even worse. It's awful with respect to spectral content. And so one idea comes up is to treat this as a probability distribution that you sample from. And if you sample from it correctly, you can turn something on or off. And so this looks really bad, but it is actually the closest in spectrum to the original representation out of all of the others, and it's because it's randomly selected. We have aliasing, no question. However, what we've done is purposefully destroyed that concentrated structure when it does alias. And so yes, we have noise that will alias in, but it's not that bad. And so yeah, back to picture number 11 there, that has, I think, the best of both worlds. It is the lowest bandwidth representation, so the easiest to solve for. Let's go back to that picture. The easiest to solve for. However, it is also dithered to destroy the higher order spatial harmonics that may come from that system. And, right, yeah, this very cool. Thank you. I appreciate the question because I obviously like talking about this answer.
But I like the results that are coming out.
I think the results are coming out of it too. Actually, so one picture that I don't have here is some of the new results we've had about 2-pulse systems. I think we have a good answer that isn't just the autocorrelation of 2 pulses, which is the one that really wants to give you. I think we're getting really close to that. So. Any signal processors that might want to ask about? I heard about correlation a lot, but didn't see FFTs. Maybe no. I thought I heard it. That's okay. It exists.
Why did you not do it?
There you go. You can. It's totally okay. I just wanted it to be the sum of a problem that already existed. Both approaches are completely valid. You can actually write this then as another quartic problem, but it's a quartic problem over the time representation, not the spectral representation. So it totally exists. The only thing that stinks, sometimes you're going to be really careful about your boundary overlap conditions. People who are familiar with processing with FFTs are intimately familiar with this. FFTs are circular. That means that they wrap, and that means that negative lag and positive lag are the same concept. And so you have to adequately pad, or in the case of a spectrum, you have to adequately oversample to produce an answer that isn't degenerate. A little bit of that. Okay.
For those of us that are signal processors and not optics people,
Yes.
the mask, can you explain the mask and how it's used? Because it's a really pretty picture,
Good.
cool designs, but like, what do you do with that?
So the mask in this system, what we'll do, I'm going to find a really basic cartoon. This is the one I always have to return to. This one here. Okay, so what the mask does is a pulse will come into the system and hit something called a grating. Now, a grating, you should think in your head, is a lot like a prism. What it does is it bends the reddest and the bluest portions of the light out spatially into an actual spatial domain where we can apply a modulation. What our mask does is it sits in this domain and chooses to chooses, it's like a mask. So in a way, a mask chooses, but it multiplies our spectrum, our actual frequency content by a number. And in the case of just a blocking mask, it's a number between 0 and 1. But there are other masks that exist that can do complex numbers. And so we actually provide the complex portion of that multiplication by moving the second grating. By the time it leaves that grating, the pulse has been recombined into a single pulse, but this time there's some funny business that happened to its spectrum. And we know that stuff. That's our a priori. So our mask then is very selectively trying to multiply that spectrum by known values.
And you've actually got the colors correct.
You know what the one that really boggled me? So this was a minor note in my thesis. I went back to correct this picture 4 times, right? So this picture here is just introducing aspects from chapter 3 in the same hierarchy of problems that we presented here today. And for broadband systems, is red the color that gets scattered most in diffractive imaging, or is blue? The answer is red, but to convince yourself of that took all of my background in phased arrays as to where squint will actually bend light. If you're steering a wideband array and you're trying to go at a really extreme angle and you have like 2 gigahertz and an 11 gigahertz carrier, 9 is going to be steered way farther than 11 is. And so that's sort of the analogy I've used there, but my goodness, was that numbers. But the order of colors is right.
So back to the mask again.
Yeah,
Let's go. So you spread light out into a spectrum. And so you have a 2D, are you spreading out into a 2D area?
It's 2D by consequence. We would really like it to not be. It would be awesome if it were one-dimensional. It is in fact 2. At that stage, the smallest point that you can concentrate it to is something called the diffractive limit, which is a combination of your wavelength and something called numerical aperture, which is based on your system overall angular bandwidth. Now, when it's concentrated to that point, it is a point in 2 dimensions. And inside this system, what we've done is we've spread out that point as best as we can in 2 dimensions. It still has a vertical direction to it. It's a narrow little Gaussian. I actually might, a moment. I have a little picture of that. I hope I do. Freezing up a little bit. My bad. There we go. And if it's not there, it's in the thesis. I can pull it up. But the idea is it is in fact a 2D slit. I'm just going to go back to the Smithy picture. There we go. It is like it is as close to one-dimensional as you can get. It does have some breadth, which is one feature of the mask. It's not painfully apparent at first that we do, is we actually keep it consistent over the vertical profile of that pulse. So if you look, everything inside one of these little squares, one of these little rectangles, is perfectly up and down. And that's because, exactly as you say, I am scared of modulating the bottom portion of the pulse differently than the top version, which was something that could have been a factor. I don't think we've seen anything super strong that proves that that's the end all be all what happened. I would really like it to be the case though. If you modulate the bottom of the pulse differently than the top, that you get different modulation spatially, because when this tries to adapt to spatiotemporal, it would be really nice if we could spatially change how we spectrally modulate.
So when you push it, when you modulate with a single measurement, what portion of this mask are you using in a single point? Or am I totally off basis and not making any sense?
You're totally fine. You're using one square at a time.
Okay.
And so a little
All right.
motor stage is actually pushing this for unique measurements. So we basically, it's like everybody pose for a picture. You have one consistent rectangle. You run it through, pulses through, you get an average over what that actual second harmonic generation energy is, and then you move the motor stage to the next one. And then you move the motor stage to the next one. You get a series of measurements. Those measurements are the H sub I and all of the equations that I've been looking at. So in this case, it's all of these guys, right? And so we start with some initial random initialization of X and Y. Fun fact, if you start with 0, this entire thing falls apart. So there are some initializations that we can't use, but otherwise it's the same.
Thanks.
Thank you.
Anything else?
And if you had more time, what do you think you would have continued to move towards this research?
Taking longer. This is the best way to use more time. So the spatiotemporal stuff is like, it's so awesome to actually stick to. It really is where people want to go, because people care about that symmetry immensely. Like the people that do fusion, they care about a spherical wavefront that actually compresses matter, because that's the only thing that will do it. So I think that that part's really cool and practical. And if I had more time, then it really would have been between that and trying to get something with higher order harmonics off the ground. The problem is that what may be interesting sometimes mathematically may not be interesting physically. I think we have an approach idea that might be able to combine second and third stuff. So you measure energy from multiple harmonics and you try to back it out. But the unfortunate problem is that physically, one of those things is much louder than another. So even if you got a result, how useful is it? But yeah, if I had to pick something to work on indefinitely, the theoretical aspects of this problem, trying to understand what restricted isometry is for this problem when you only care about being rank 1 and beyond second harmonic nonlinearities. Thank you for the question. Oh, okay, sorry. Oh, you had a question. Gotta put you on the spot, ma'am.
What are you making me for dinner?
Meatloaf. I know how much you love that.
All right, I think if there's nothing else, why don't we give Dan a before we get the studio audience a chance to escape. Got it. I appreciate it.